Hello everyone, I am Pradipta Jana, final year student of M.Sc Applied Geology, Department of Earth Sciences, IIT Roorkee. Today I am going to present on the topic interference or superimposed folding under the guidance of Dr. Sandeep Bhatt, Assistant Professor, Department of Earth Sciences, IIT Roorkee. So here you can see some field photographs of the folding. As you can see, these are complex type of folding. It can't be explained by our traditional type of understanding of folding. So here the concept of the interference folding. So in our presentation, we will discuss about how these interference folds are formed. Let's start. Now, before jumping into the classification of this type of folding, let's see where this type of folding can occur. First one is the crossing orogenic belts. This type of folding can form in layered rocks which suffer successive deformation, which is separated by very large interval of time. The second one is successive deformation in a single orogeny. In one orogenic cycle, this type of folding can form when the compressive deformation occurs in separate pulses. And the next one is the successive folding during a single progressive deformation. It can happen that during a single progressive or continuous deformation, the orientation of layering with respect to the axis of the incremental strain ellipsoid can change. In that case, this type of complex folding can occur. The last one is the synchronous folding in different directions during one deformation when the computer lens is under influence of two-dimensional constrictive strain due to three-dimensional constrictive strain. Under this condition, folding can happen in several directions synchronously. Now let's see the classification of interference fold. It is given by Ramsey and Hooper in 1987. They considered that there are two generations of folds that got merged and give this superimposed fold. By classifying to classify this type of fold, they take two parameters. They take the angle between the fold axis of the first generation fold and the fold axis of the second generation fold, and the angle between the first generation fold axial plane and the deflection direction of the second generation fold. And both the angles that is between 0 degree to 90 degree. There are four end members of this type of folding classification, that is type 0, type 1, type 2 and type 3. As you can see in this classification, they appear in the corner sides of this classification. Here it is basically shown the horizontal cross section of this uh, occurrence of this fold, and the others are basically the in between members of this folding. Let's discuss about the first type of folding is the redundant superimposition folding. Basically, here there is no difference between the first generation fold and second generation folding, as you can see in this picture. Basically, in this superposition, the fold is got tightened. In the first generation fold, here is the fold axis F1, first generation fold axis, and the axial plane 1 AP1 of the first generation fold. And here B2 is the fold axis of the second generation fold, and A2 is the deflection direction of the second generation folding. By merging these two type of folds, we get the resultant fold geometry. Okay. And basically, they are plane cylindrical fold. That means the axial plane and the hinge line is not curved. The axial surface angle is 180 degree and hinge angle is 180 degree. Now, what is the axial surface angle? If we assume it is a axial surface, then if we draw tangent from here and tangent from here, we the angle in between them is the axial surface angle. It is the same concept as the interlinked angle. And what is the hinge angle? If it is a hinge line that is curved, if we draw a tangent from here and tangent from here, the angle between them is basically the hinge angle. So in this case, as it is a plane cylindrical fold, the axial plane and the hinge angle, a hinge line is not curved. That's why both are 180 degree. And here you can see again a picture of the initial fold and the resultant fold, and the angle between A2, which is the deflection direction of the second generation fold, and axial plane 1, which is the axial plane of the first generation fold. The angle between them is 0 degree, and the angle between A2 and B2 plane and fold axis of the first generation fold is also 0 degree in this case. Here is the geographic projection of this kind of fold. So here also you can see first generation, second generation fold and their resulting fold. Here a field of photograph of this type 0 type of folding. The next one is the dome and basin pattern. Basically, they are plain and non-cylindrical fold. As you can see, here is the first generation fold, second generation fold, and there is a resultant fold. Uh, and they, as you can see, they form a dome and basin type folding. And the axial surface angle here is 180 degree, but the hinge angle is not 180 degree, as here is the hinge line is cut. And the angle between A2 and axial plane 1 is 0 degree, but the angle between AB2 plane and the fold axis is not equal to 0 degree. Here also again I pictured the first of the generation of folding and the resulting fold. And here is a stereographic diagram, stereographic position diagram of this trigon of folding. And here the outcrop if we see it is oval, somewhat rhombic, and lozenge shapes outcrop can be seen. Now here also here is the first generation fold, second generation fold, and their resultant fold. Here is a schematic diagram showing how this type of folding can occur in a field. As you can see, a somewhat oval type outcrop can be seen here. Here is the original field photograph of this type of folding outcrops. The next one is the type 2, which is a crescent mushroom shape pattern. Basically, they are non-plane, non-cylindrical fold. That means the hinge line and also the axial plane is curved. Here the first generation of fold, here the second generation of fold, and by superimposing them, we get the final generation fold. Here the axial surface angle is not equal to 180 degree, and the hinge angle is not equal to 180 degree, as they are both curved. And the angle between A2 and axial plane 1 is not equal to 0 degree, and A2 B2 plane and fold axis is not equal to 0 degree. Here also here is the first folding, and here is the final folding. And here is the stereographic diagram of this type of folding. This kind of show the crescent or mushroom shaped outcrop. Here also the first generation of folding, here is the second generation of folding, and here we got the interference of this folding. Here again a schematic diagram showing how the outcrop works. We can see a crescent shaped outcrop or mushroom shaped outcrop is seen. Here is the original outcrop of the this type of interference folding. Now, next one is the type 3 or convergent or divergent pattern type of interference folding. They are non-plane cylindrical folds. That means it has uh, straight hinge line but curved axial plane. Here you can see first generation fold and second generation fold and their interference fold. Here the axial surface angle is not equal to 180 degree as it is curved, but the hinge angle is 180 degree as hinge line is straight. And the angle between A2 and axial plane 1 is not equal to 0 degree, and the angle between A2 B2 plane and fold axis of the first generation fold is equal to 0 degree. Here again a picture showing the first generation of fold, and it is the resultant one. And here is a stereographic diagram projection of this type 3 of fold. And these two basically hook shaped outcrop. Here also the first generation, second generation fold, and due to their interference, this type of folding you can see. Here is schematic diagram showing how field outcrop of this folding occurs. As you can see, it is like of the hook shape. And here the original field photograph of this type of folding occurs, and you can see hook shape here. Now let's see different modes of superimposed buckling. Basically, it is given by the Ghosh and others, and it is divided in case of single layer and in case of multi-layer. If we are talking about superimposed buffering in a single layer, It has the four kind of modes. Let's discuss the first mode. It happens when the primary fold, that is F1, is very gentle and with a large interlimb angle is about greater than 135 degree. And the next fold F2, which is roughly of same size of F1 in this case. And if the first generation fold and the second generation fold is basically perpendicular to each other, they form the dome and basin structure, as you can see in this diagram. And the next one is the if they are oblique, that means first generation fold and second generation fold at an angle to each other, they form the elongate domain basin structure, as you can see elongated folds. And if you see this diagram, here is a horizontal cross section of the this type of folding, and you can see ellipsoids here. If we notice the long axis of this ellipsoid, they are not perpendicular to the shortening direction in case of first generation fold and the shortening direction in case of second generation fold. The long axis is not perpendicular to the both of them. So if the shortening is large and the stretching perpendicular to the layer is more, then we have the generation of C4. Now let's discuss the second mode of superimposed buckling. Basically, when the first generation fold has a moderate tightness, when the interlimb angle is about 90 degree to 135 degree, we get this type of buckling. Here the F2 folds are much smaller in size than the F1 folds. As you can see in this picture, they are much smaller in size, while the first fold is bigger in size. And the smaller folds are right in the hinge zone of the larger F1 fold, as you can see in this picture. The third mode of the folding is basically happens when the initial fold is moderately tight. Interlip angle is less than 90 degree, but it is not very tight or isoclinal. And if you see the picture, here is the third type of superimposed buckling. If you see here, there is synform can be seen. The synform of the F2 fold is basically is in one limb, and the other limb we get the antiform of the second generation fold. So we get the synform and antiform in the different limbs of the first generation fold. And basically, with progressive tightening of the F2 synforms, it basically progresses across the F1 antiformal hinges. And if the F2 antiforms progress, it also cross the F1 synformal hinges, and this leads to development of sinuous hinge. As you can see here, it is a first hinge line of the F1, and here is the sinuous hinge line developed after the progressive tightening. And the at the point the at some point when the progressive tightening occurs, the initial upward convexity of the layer changes to upward concavity. Basically, they form the type 2 interference pattern. As you can see, the dotted is the first um, mm, uh, previous hinge line. Here A1 is the point as synform, and B is the point in antiform location. But due to progressive tightening, A point comes at A dash and B point comes at B dash. And with progressive tightening, A dash point comes this side and B dash come this side. So basically, we had the conversion of upward convexity to the upward concavity style. The next one is the fourth mode of superimposed buckling. When the initial fold is very tight or isoclinal, this type of folding can occur. But the second deformation events involves shortening along the F1 hinge line. As you can see, the hinge line is curved and the shortening along the F1 hinge line is occur. But no hinge replacement can be seen during this deformation. And this type of deformation can produce type 2 or 3 in folds. Basically, if the second deformation involves a flexural Then the angle between early and late fold, basically the first generation fold and second generation fold axis remain constant at different parts of the structure. But if we includes flattening also, that means flexor and flattening both can be seen, then the angle may not remain constant. As you can see, here is a schematic diagram. Here is the early fold hinge and here is the late fold hinge. Here is it is so. Let's discuss about superimposed buckling in multi-layers. It is also given by the course and others. But in the case of thin multi-layer, the superimposed buckling happens in the four modes as the single layer. But the difference comes in the second mode, where we can see the arc length of the uh, uh, fold 2 second generation fold is much smaller than the first generation fold, less than one fourth of the the second generation fold is more than one fourth of the first generation fold, and the small folds, as you can see here, the second generation fold are quite small inside. And second can happen that the small fold was able to overprinted at the long limbs of the first generation fold, but it does not appear their hinge area, as you can see in this picture. But if they are the multi-layers are thick in appearance and they have different in mechanical properties, then complex type of uh, folding can occur that leads to the disharmonic folding basically. And as you can see here, a disharmonic folding can occur. Here is the thin layer in the upward, and here is a here we can see the thick layer. So, due to this superimposed buckling, we can see that the thin layer, which is more competent in nature, so it's the third mode of the buckling, and where the lower thick layer, so it's the dome kind of structure. And if we see the next generation, next type of folding, as we can see the thin layer, which is competent layer, and the lower layer, which is thickened layer, both generate second mode of buckling. As in the right side, their gap is shown to show the occurrence of the thick layer. The next one is the you can see here the thin layer incompetent sorry more competent thin layer is basically folded in the third mode, and the thick layer it is folded in the second mode of folding. So, if we move forward, here this type of folding can occur where the more competent thin layer is basically buckled to follow the fourth mode, and the thick layer is buckled to follow the third type of folding. Now, in field work, let's discuss how we can identify that the region suffered this type of uh, different deformation to fold the superimposed folding. There are lineation and cleavage, which helps in understanding these overprinting relations. As taken example here, is a fold is developed, and here the elevation is developed parallel to the hinge line or fold axis. If the region suffers another deformation, the lineation also become deformed. That is an indication of this different type of deformation the region suffers. And again, we have a fold here, and S1 basically is the uh, axial plane cleavages, which is parallel to the axial plane, is occurred here. If the region suffers another deformation, then the axial plane cleavages also cut, which is also an indication. As you can see also in this diagram, here is the early fold nose, and here is the axial plane cleavages S1 can be seen, and it suffers a second time deformation, and the axial plane of the second deformation is H2 can be seen here. This in this case also we have a first generation fold, which axial plane uh, cleavage is S1 and it suffers second generation folding, and due to this we get the H2. This is the second generation of axial plane. So that's all. And here is the reference from which I have made this PPT. And thank you.